Hello, Math 2412 pre-calculus students. Here's my fourth part of Basics of Trig for calculus students. This is going to be about two more trig functions and a really good way of thinking about why they're called what they're called, how they're defined, that generates a couple more identities which you're going to need when you're in the calculus. And this is a very handy picture for remembering those key identities having to do with these two new trig functions. All right, so if we go back to our unit circle picture and our angle theta in standard position, generating a point p sub theta, you drop the perpendicular, you get q sub theta, and then using the kind of triangle this is, you generate what the lengths of the sides O to Q are and P to Q, and from that you get what the coordinates of P sub theta are. And that works anywhere in any quadrant. Okay, on top of that, if we attach what's called a tangent line to the point R, which was the point 1, 0, if you recall. Okay, I think I had that on a previous sketch. Let's just call the point 1, 0 R for the following reasons. Because with each theta, I generate a P sub theta, a Q sub theta, there's R, and now I'm going to go up the tangent line where the tangent line intersects that ray, the terminal ray of theta. We're going to define that to be the point S sub theta. So O, P, Q, R, S, right? Okay, one thing about tangent lines. Tangent lines meet a curve at right angles. So if I take this picture of these two nested, there's two nested triangles there, and guess what? They're both right triangles. I'm going to take that picture here, blow it up here. Because that was a tangent line, this angle, ORS, is also a right angle, okay? So now I have two nested right triangles, OPQ and OSR. Notice that these two right triangles share not only the fact that they have a right angle there at Q and at R, but also that at O, a point they share, they have the angle theta. So that means these two triangles, let me pull them apart. Here's OPQ, here's OSR. They are similar. That little symbol is saying they're similar. What do you know about similar triangles? That if you take the ratio of two sides here, the value of that ratio is equal to the value of the ratio of the corresponding two sides over here. And also, going back to this picture, the angle theta. Notice how where S sub theta ends up is a function of how big theta is. If theta was smaller, S sub theta would be smaller. Notice if theta was 0, for example, S sub theta would be right on top of R. We define this bit of the tangent line cut off by the angle theta. We call that the tangent of theta. So that's where that name comes from, or a good way of thinking about it. The tangent of theta is that length from R to S theta, all right? So when we have these two nested right triangles here, when we take them apart, put them right next to each other so you can see what's going on, the lengths of the sides of OPQ are cosine theta, sine theta, and 1. Now that's only true over in this picture because here theta is between 0 and pi over 2, right? That's the only reason I can assume the length of this side, OQ, is equal to the cosine. The cosine is not always positive. The sine is not always positive. But in quadrant 1, for angles between the quadrantal ones, you definitely have that the cosine and sine are positive. Okay, so that I'm in this first quadrant means that I can label these lengths of these sides of OPQ with cosine and sine. And of course, the hypotenuse is 1. OP is 1. The other triangle, which also shares theta at O, OSR, has this length from S theta to R, which we've defined to be the tangent of theta. And now here's some more etymological history, we call O to S the secant of theta. Where did that come from? A secant line, let's see, can you guys see that? A little history there on the word secant. A secant line, yes, you can see it now. Just like the word second, having to do with the number with 2, a secant line cuts a chord or a curve in 2 places. A tangent only cuts it in 1. It's at right angles there. A secant line can cut a curve in all kinds of different angles, but the big point is it cuts it in 2 places. So thus the word secant, like second, having to do with 2. So that line, that secant line, which is OS, that's the line OS there. Also, same thing as OP, right? That is a secant line. So the distance from O to S theta gets called the secant of an angle. Okay. So we have this O to S theta is secant, S theta R is tangent. Why is O to R equal to 1? Because O to R, remember, that's just the distance from the origin 0, 0 to the point 1, 0. That distance is clearly 1. So now I have these 2 triangles are similar. So I have all kinds of relations about ratios of their sides. For example, the tangent of theta side to this side here, 1, should be the same thing as the ratio of this side to that. And that's where we get this ratio. Tangent of theta is to 1, tangent of theta is to 1, as sine of theta is to the cosine of theta. Well, we just take that as our definition. The tangent of theta, from here on out, in calculus, it's just best to think of the tangent theta as the ratio of the sine of the angle, sine of theta, to the cosine of theta. Okay. Here's a relation, the fact that comes out of the fact that these 2 triangles are similar, involving the secant. The secant is to 1, as 1 is to the, what goes in here? Secant of theta is to 1, as 1 is to the cosine of theta. That is what we're going to take as our definition of the secant of theta for any angle. Same thing with tangent. These definitions are true for all theta, not just the ones in the first quadrant. This is why we take it as definition. The secant of theta is always 1 over the cosine of that angle. So if we know the sine and cosines of those angles, we know their tangent and secant. For example, what's the tangent of 5 pi over 4? You see, if a calculus student for some reason suddenly needs that, you'll see them drawing the unit circle, putting 5 pi over 4 in standard position, right? There's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So there's your angle 5 pi over 4 in standard position. There's your p sub 5 pi over 4. If I blow this up over here, I've got here's p sub 5 pi over 4, here's q sub 5 pi over 4. Oh, that's giving me a 45, 45, 90 triangle with p in quadrant 3. So yes, using the fact that these lengths, if this length is 1, this has to be square root of 2 over 2, which, if you remember, that was the same thing as the square root of a half. Okay, just reminding you of that little fact. And so therefore, thinking about that point in the third quadrant, p sub 5 pi over 4, oh, its coordinates have to be minus the square root of 2 over 2, comma, minus the square root of 2 over 2. Remember, square root of 1/2 is the same thing as square root of 2 over 2. So, but this is how I would write it if I was giving that as a final answer. But I'm not. Remember, this is the cosine of the angle. This is the sine. So the tangent of 5 pi over 4, using its definition now as always the sine of theta over the cosine of theta, equals the sine of 5 pi over 4, which is this number, over the cosine of 5 pi over 4, which is the same number. So this just turns out to be 1. What about the secant of 5 pi over 4? While we're here, why not pick that off? All right, so the secant of 5 pi over 4, going by this definition now, the secant of an angle is always 1 over the cosine. So the secant of 5 pi over 4 is 1 over the cosine of 5 pi over 4. Draw the picture, get the information that the cosine of 5 pi over 4, the x-coordinate, is a square root of 2 over 2, a negative square root of 2 over 2. But I notice that this time I'm not going to use that. I'm going to call it a negative square root of 2 over 2, a negative 1 over the square root of 2. Why would I do that? Because I have to take its reciprocal. And taking the reciprocal of 1 over something is dead easy. 1 over a negative, 1 over the reciprocal of 1 over square root of 2 is just a negative square root of 2 over 2. It's negative square root of 2, period, full stop. You'll notice this number is greater than 1. The tangent here was equal to 1. This is the first time we've had a trig function have a value greater than 1. Yeah, for the tangent and secant, do not be surprised if those values exceed 1. Unlike the cosine and sine. Remember, they're constrained to be bounded by negative 1 to 1 because they are just x and y coordinates of points on the unit circle. But the tangent and the secant, sky's the limit. All right. Next will be part 5 on 2 more trig functions.